graphing tangent and cotangent.
Yeah, I was confused.
Those are wait, we haven't done them before, so this is all kind of newfangled. Very true. Here's how I'm gonna tackle it. We just talked about tangent on the unit circle. You just have to know the basic values, which are if I just write them in right now, I bet you can get all of them. It's 1 over the square root of 3 for the 30 degrees. It's 1 square root of 3. It is 0 and undefined. And the others are same on the third quadrant, negative opposite sign. In the other two quadrants, we'll just use that pattern to our advantage, okay? So when I say what's the tangent of 0? It's definitely 0. Pi over 6 is that 1 over the square root of 3 I mentioned, or square root of 3 over 3 if you prefer, that's fine. There's 1, and square root of 3, Nathan, square, hold on. All right, undefined. Back to, now, I'm not going to fill in the remainder of those. I could. If you wanted to go to 2 pi, I guess I could. Let's go to 2 pi over 3, since we know these so well. Now, 2 pi over 3 is where it changes to negative square root of 3, because it's the same sine and cosine as we had at pi over 3. It's just one of them's negative. So it's just a negative square root of 3, then it's 3 pi over 4. As we descend in that third quadrant right there, we're at negative 1, and then we get to 5 pi over 6, and our tangent is negative 1 over the square root of 3. So those values, I'm not going to plot them super precisely, but I'll put a few in there and then show you it fits the shape that you need to know a little bit about for tangent. Pi is 0, so the tangent at pi is 0. Straight down at 3 pi over 2, we're going to jump a little bit. It's undefined. And then when you go to 2 pi again, we're facing straight right, and tangent is back to being 0 again. That should do it. That's enough to get you the basic graph. Then what you notice, it's where it's undefined, like pi over 2 and 3 pi over 2, those are our vertical asymptotes, and they're always, whatever the width of your vertical asymptotes are for any two, then it's the same to all the rest of them. They repeat. So negative square root of 2, or negative pi over 2, and negative 3 pi over 2, etc. So you'll just have this repeating vertical asymptote. And what happens is, if I plot these in here, the other points, you'll see it squeezes between those vertical asymptotes. So tangent hugs those asymptotes. When I put in 0, I got 0 for my table. Right? That was 0, 0. Pi over 6 is 1 over the square root of 3. Now, if you want a decimal for that, you're welcome to go find it. But when you go to pi over 4, 1 over the square root of 3, when you go to pi over 3, you get a little bit further up, and what happens is you get this general increase until you hit the asymptote, but the graph snuggles up against that. And as you descend the other way, it's the same values, it's just going down the curve. Again, I'm being less precise just because I want you to have the general sense of, you know, the graph, and I want you to see that if you are to plot those values that we got from the table, they will match that general sense graph. That's what you need to know for tangent. Now, what's interesting is that every time you go over to like pi, for instance, didn't we put pi in? Pi gave us 0. Well, the graph repeats itself. If you put in some other values that I've left blank in here, so if I do, for instance, like 7 pi over 6, if I do 7 pi over 6, which is facing right here, that is a tangent of, remember it's 180 degrees away, they're the exact same. That'd be 1 over the square root of 3 again. So it's the same thing I got from my previous graph from putting in pi over 6, which is right about here. I'm getting the same value. This graph repeats itself. It's one of those that has the same over and over again, and it snuggles those asymptotes. And then it repeats itself again, over and over again. Tangent goes forever and ever repeating this pattern. That's tangent. And it has an odd symmetry. And there's vertical asymptotes that are actually pi apart. The distance between these is a distance of pi. It's like a half circle, about 180 degrees apart. Now when you do cotangent, this one isn't quite as cool. It just takes the reciprocal of all the values. You know how that works. So if I go to my table from before, I flip them. 0 flipped is not 0. So when I flip that 0 up there, it actually becomes undefined. And the other one to note is where it was undefined before, that's the fact that I'm doing 1 divided by 0. When I reciprocate it into my cotangent, it actually becomes 0 here. So those trade places. And so if you can find those first, that's helpful. That 0 becomes undefined in my reciprocal function. The undefined becomes 0, etc. The 0 becomes undefined. So this 0 goes undefined. Now, the reason I put those in there is you're going to find out that you end up with a lot of the same values. Watch what happens when I reciprocate the rest of them. I get 1 over the square root of 3 becomes square root of 3. 1 stays 1. And square root of 3 becomes 1 over square root of 3. They swap. It's like they trade heights. And what that means graphically is it just faces the other way. It has a little bit different location. It has a little bit of a off kilter. So I'll go plot them over here on the side real carefully. First we got to do our asymptotes. 0 is an asymptote because it's undefined at 0. So I go over to 0 and I do, oops, I'm sorry. Like that. And then what was the other one? Pi. They're pi apart still. 2 pi. Like that. At pi over 2 is 0. And pi over 6 was the square root of 3. And pi over 6 is the square root of 3 is like, if you've done the square root of 3, it's smaller than 2, so it's up here somewhere. You end up with that same kind of graph we had before, just facing the other way and off kilter a little bit. 3 pi over 2 is 0 in our graph. If you want to plot more precisely, you certainly can. But they're off a pi over 2 and they face the opposite direction. Just the general understanding of their shape is plenty. And that's it. That's all I wanted to show you, the connection between those graphs. Because eventually you'll encounter those in a different case and see if you can make that useful at that time. All right. So Claire, we got to do inverse trig and inverse sine and inverse cosine. These are weird, and inverse tangent. I put these on here because, ladies and gentlemen, if you'd pause, talk later, you can chat later. Put your phone away if you have it, the 4 of you that do. Here's how I'm going to get inverse sine, a little less conventionally. We just graphed this a minute ago. I want you to graph sine first. So if we graph sine first, that's sine of x. I have pink, so I can put it in pink. If you keep going with it, then it's up here, and it's back down, sine of x. To do the inverse function, some of you know how this works, but it is y equals x. Folks, I don't have a lot more patience. Hush, or you're going to have to go. Now, if I take and finish this up, y equals x, that's the line of reflection that we use when we do an inverse. If I flip and rotate this, one of the shortcuts you can think of for inverse functions, they're hard to do unless you're one of those really talented folks that can see a reflection over that green y equals x line. Some people can, and they're really good at it. And in fact, my scale is not even drawn properly. This is an approximate. The way this is scaled, it's not exact. But what you should know is that anything that goes up ends up facing to the right. Anything down ends up facing to the left. Anything right turns up, and anything left faces down. They trade places. Do you remember x and y swap in an inverse? So if you trade x and y, they'll literally trade all the x and y coordinate points. Any point that was like a negative y becomes a negative x. So something that was down would end up facing left, in a sense. The only reason I say that is because see how this graph flows left to right? After you invert it, it'll flow up and down. It just trades any pattern that you see or any motion you see to the left and right after inversion will go up and down. So all you have to think of is where they meet at that inverse or that swap, that y equals x line is right here at the origin. And then they also touch right up here. After that, I'm just going to draw my sine curve up and down the y-axis. It's kind of cool. But if I do it reasonably well, you can kind of see the pattern. I'm not really good at this, but I'll try. All right, it's getting worse and worse the more I scribble on there, but be patient. I'll get it. There you go. So something like that. Not pretty by any standard. Now, that is not a function. It's not. So what happens is, I'm interested to show you, your calculator does do this. I'm going to pull up TI Smart View and let you see what it shows you. When I do inverse sine of x, it'll graph it. But it doesn't graph this whole blue graph. It only graphs a chunk of it. And there's a good reason for it. It gives you a sense of, your calculator knows that if I graph the whole thing, it's not a function. Your calculator likes to only graph things that are functions that pass the vertical line test. So it chops it down a little bit. So here comes, if I can, I'm going to get my little highlighter and show you what part shows up. And Smart View's got other priorities today, so it's going to do its own thing. All right, here we go. Got to be in mode radian because that's what we're graphing in right now, if you want to follow along. And then I'm going to clear this out and simply hit second sine and x. And if I graph it in the special zoom trig window, if you've ever tried that, zoom 7, it's usually a good window for this kind of thing. Look at that. It only graphed a piece of it. It's just a little sliver. That little sliver is actually the only part that you get for, we use inverse sine. Remember when we were trying to solve for theta the other day and those like word problems like, hey, what's the angle of elevation? And sometimes you had to go arc sine of both sides, sine to the -1. The answers that you will get from your calculator are only the values you see here. They're between -pi/2 and pi/2. That's a little bit of a problem. It only spits out answers from -pi/2 to pi/2 that are within that range. So this is going to be kind of cool for you to see how this plays out later. But your inverse sine function is only the part that goes from here to here that I'm highlighting now in yellow and getting darker and darker and darker. I hope that shows up. I should pick a different highlighter color. But it's only that little chunk. But I have the graph up there too so you can see it. The same goes for arc cosine, so I'm not going to make a big deal out of it. You can graph cosine and then flip it. So instead of going down the x-axis, it's going to go up the y-axis. And the only part of it that the calculator recognizes that makes it still a function is, so we're going to cut to the chase. Just go arc cosine, second cosine. Hit entrée, s'il vous plaît. And graph, because we had a nice window. It's like the upper chunk. It's like from up top there, so it's an upper chunk, yeah. That I'm sure Graham will learn along the way too. That's a great phrase. So this part, it only graphs a part of it from here to here as well. It only spits out answers from -pi/2 to pi/2 as well. And you can use the sliver on my graph, or you can use my horrible sketchy sketch. It's about as sketchy as that gets. Ugh. Maybe I can erase pieces of it. And then arctangent is way cool. So those are the pieces that only graphs a small piece of it, and that's okay. And I want you to know that that exists. Arctangent, if you take a tangent curve, watch this. This is tangent in blue. And I'll graph several of them. This one's fun. Dun, dun, and dun, dun, like that. If you take that and inverses on a large scale, this is again kind of an approximation, it takes what's going left and right in the patterns and it changes it to going up and down. So what, instead of these being kind of vertically side to side, when you invert it, it stacks them up on top of each other. So the inversion of this, so the inverse function, actually has asymptotes that are instead of -pi/2 and pi/2. The asymptotes are horizontal lines that are pi/2 and -pi/2. And the graph is on its side instead of being vertical. I think of that as being on its side anyway, horizontal like that. So it takes, oh, I'm sorry, you guys have that graphing calculator in front of you, but that's the pink portion. That's it. Now, do we graph a bunch of them? Do I stack them on top of each other? Would that be past the vertical line test if I stacked them? And no. So your calculator, and when we do